12 days from now, a visitor from deep space will pass by the Sunday. It's called 3I Atlas, and it weighs 33 billion tons. It's hurtling through space at 80 times the speed of a bullet. In that moment, everything around us could go awry. Its orbit is almost parallel to the plane of the solar system, something no natural comet has ever done. A question arises, quietly but terrifyingly. Is this a natural visitor or a machine sent to break before the sun and stop inside our solar system? While Earth's eyes are blinded by the sun's light, the only thing we know is what will appear on the other side. Like this video and subscribe to the channel. That's how you help yourself continue to bring soothing science stories to your sleep. The real danger is in what we cannot see at the very moment we need to see it. 3I Atlas is hurtling toward the sun at nearly 55 kilometers per second through an orbit that defies all probability. Instead of coming in at a random steep angle, it glides along the plane of the solar system, tilted just 5 degrees to the ecliptic, the invisible disk where the planets orbit the Sunday. For someone from interstellar space, this is an extremely rare exception. Random objects should come from all over the sky. But Atlas is different. Its orbit matches almost perfectly with the planet lane, as if it were drawn deliberately. The ecliptic is just a thin slice of the celestial sphere, like a thread across the sky. For a comet to come within 5 degrees, it's like throwing a dart at a spinning globe and hitting a small city street. The previous 2 interstellar visitors, Oumuamua and Borisov, both came from high angles. They cut across the solar system like sharp streaks of lightning. As for Atlas, it's drifting against the planet's rotation, but it's almost flat on the ecliptic. That alignment isn't just interesting. It completely changes what can happen. When Atlas reaches its closest point to the Sunday, an object approaching the sun along the ecliptic would meet it at a very shallow angle, extending the time it's under gravitational influence. If someone wanted to take advantage of the Oberth effect, the boost effect, when firing engines at their highest velocity, this is the perfect geometry to do it. Atlas was discovered on the 1st of July 2025 by the Atlas telescope in Chile. It is the 3rd interstellar object ever confirmed. The speed of more than 200,000 kilometers per hour proves that it is not bound by the Sunday. And on the 29th of October 2025, it will be closest to the Sun at a distance of 1.36 AU, that is, within the orbit of Mars. If you are still awake, please leave a comment. Just one line is enough to let me know that you are looking up at the night sky with me. According to orbital mechanics, Atlas would have passed and disappeared forever, but its peculiar orbit and extremely high velocity raise the question: is this just a coincidence or a sign of intentionality? If Atlas is natural, it is just a rare visitor that we can explain. But if not, then the geometry of its orbit suggests a calculation that goes beyond chance. At perihelion, Atlas will be traveling at nearly 68 kilometers per second, twice as fast as the fastest human spacecraft. This is the moment. The laws of orbital mechanics open up a special gap. The Oberth effect, first described by Hermann Oberth in 1929, states that the efficiency of an engine burn increases dramatically when it is performed at high velocity, deep in a gravitational field. The same thrust if you burn it in deep space. You get a tiny bit of energy, but if you do it while passing the sun at 68 kilometers per second, the effect is multiplied. Just a 1 kilometer per second change would be enough to completely alter the orbit. To be held back by the sun, Atlas would have to slow down by about 20 kilometers per second. A nearly impossible requirement with any known technology. Comets naturally change their orbits slightly due to evaporating jets, but that force is small, chaotic, and not precisely directed. If there were a carefully controlled deceleration, it would show up in the data. Astronomers would see a sudden drop in velocity beyond the ability of nature to explain it. And that is why perihelion becomes so important. If Atlas does decelerate, the sun's gravity will amplify that effect, turning a small nudge into a huge change. The question remains, is nature or some other hand at work? If you found this story compelling, please subscribe and turn on notifications. Who knows? Maybe next time the universe will send us a new secret. For now, the only thing that is certain is absence, a lull that lasts for weeks, where dramatic changes, natural or unnatural, can occur. Beyond human observation, when 3I Atlas reappears in the November dawns, astronomers will have no choice but to follow its tracks, piece together the story that unfolded in the darkness. Brightness is often taken as a sign of mass, but this time, with Atlas, that assumption is in doubt. Refined optical measurements revealed that the object weighed about 33 billion tons, one of the largest visitors ever observed by humanity. But when planetary dynamicists ran their models after the flyby, On October 3, the results were empty. No wobble, no deflection, no trace of Mars having felt the visitor's gravitational pull. At a distance of just 29 million km, such a massive object should have created a small variation in Mars's orbit, or at least a ripple in the navigation data from orbiters. But ESA's Mars Reconnaissance Orbiter and Trace Gas Orbiter were completely silent. The Deep Space Network also detected no signals above the background. And this is not a measurement error. In 2014, the comet Siding Spring, much smaller, much lighter than Atlas, left a distinct gravitational trail in Mars's orbit as it passed by. Atlas, thousands of times heavier, passed by as lightly as a breath. This anomaly is puzzling scientists. Celestial mechanics teams reanalyze all the data, looking for every tiny error in Mars's motion and the time it takes for the spacecraft to respond. But the results are the same. There is no gravity, no phase shift, no giant solid core present. Some researchers believe that the mass has been overestimated, that Atlas's brightness is just a mirage caused by dust and an unusually reflective surface. Others think of a hollow structure or porous, as if Atlas was not a rock, but a hollow shell floating among the stars. Rotation data showed the object was rotating faster than a solid mass of that size could sustain. A bright object spinning rapidly, but with almost no significant gravity, all add up to the equation of a hollow shell, natural or made. In mid-September, spectrologists discovered Atlas carrying a tail of gas that stretched for more than 180,000 kilometers, a veil of dust and water vapor surrounding the comet's nucleus. Spectral analysis revealed that the main component was hydrogen cyanide, HCN, which was being spewed out at a rate of about 4.5 times 10 to the power of 25 molecules per second, equivalent to 2 kilograms of HCN per second. That's a lot, but it's within the natural range. As sunlight heats the ancient ice, jets of water vapor and dust shoot outward. The solar wind and radiation pressure bend into asymmetrical streaks of light, shimmering like breath. Atlas's chemistry is not only a fascinating story, but also a benchmark by which it is compared to other natural comets before perihelion. Atlas's light spectrum matches those of the two previous interstellar visitors, but its molecular ratios, reflectivity, and evaporation rates all tell a distinct formation history. For now, all the chemical data still favor the natural hypothesis, a porous ice mass rich in volatiles, is degassing itself as it approaches the Sunday. This information will serve as a benchmark so that after perihelion, we know what has changed. If the chemical structure is distorted or the tail is unusually fragmented, those differences will be apparent in the September data. But there is another theory, a possibility that many are not yet ready to dismiss. A hollow object, not made to endure, but to open. At perihelion, where light and gravity are at their maximum, it could break apart or unfold. If Atlas is built, this is the perfect time to act. Instead of breaking up in a chaotic fashion, the outer shell could split, freeing smaller units, probes, sensors that drift apart like dandelion seeds in the wind. Then, the sky would not be quiet. After perihelion, astronomers would look for discrete streaks of light, moving in an orderly fashion, not randomly like a natural comet. Some pieces might change direction or accelerate suddenly. If such movements were present, they would be the clearest sign yet that Atlas was more than just rock and ice. Avi Loeb's Galileo project is waiting for that moment. They have drawn up a detailed checklist, track any debris that has left its original orbit, measure the velocity, compare it with models of naturally broken comets. If it's all random, the story ends with nature. But if order emerges in the sky, it will shake up science. The days after perihelion will be the final test. But the sky doesn't sleep. October 29 is approaching. In the night sky, a question burns quietly. Why did NASA lie that 3I Atlas would disappear? They said it would slip behind the sun, be eclipsed, and be swallowed up in the brilliant halo of our own central star. But the sky always remembers what people want us to forget. Independent astronomers have never stopped watching, and what they recorded has changed everything. 3I Atlas is not gone. It's still there, next to the sun, brighter, faster, and breaking every prediction humans have ever written about it. So, if NASA knew, why did it stay silent? Why did it lie? Stay until the end, because tonight, we're going to reveal what they didn't want anyone to see. The truth, all along, was not in the dark. It was in the light. If this mystery intrigues you as much as it did me, please like and subscribe so that whenever the sky changes, you will be the first to know what is happening. Amateur astronomers who patiently stacked frames in their small rooms kept their lenses. At the burning Sunday, they didn't wait for permission. They didn't believe in the concept of lost signal. And what they recorded was not an absence, but a presence. Atlas wasn't hiding behind anything. It was glowing. It was moving and behaving in ways that broke all official forecast models. The first images began to appear on October 28, 29, and then 30. Not from NASA, not from the European Space Agency, but from ordinary people with telescopes and an internet connection. So ask yourself, when a space agency with a multi-billion-dollar budget and a network of instruments spanning the solar system tells you an object is unobservable, but an amateur observer in New Mexico still captures it, what does that mean? Is it an oversight? Is it a miscalculation of the observational geometry? Or is it something else entirely? The data they shared not only contradicts NASA's timeline, it also defies the physics we believe Atlas must follow. This is not just a story about a comet. This is a story about faith, about who gets to define truth when the unexplainable appears in the sky. It is a story about what happens when the guardians of cosmic knowledge tell us to look away at a time when nothing like it has ever happened. And there's also the story of the consequences no one wants to say out loud, the hints that 3I Atlas might not be a comet. You're about to see the official version, the one NASA released, and then you'll see the contradictory images, the data that shouldn't exist, the brightness curves that physics can't explain. You will hear about jets of matter that go astray, about velocities that deviate from gravitational predictions, about components that are so bizarre that scientific papers use the words extreme and abnormal. And finally, you will have to ask yourself, what do I believe? When Atlas reappears in December, if it is still on any trajectory, we will know. If the independent observers were right, we will know. If NASA is protecting us from information or protecting information from us. And maybe we will face the possibility that science fiction has whispered about for decades, that there is something out there and it is looking back. What if something isn't natural? What if it's observing us the same way we observe it? The question is no longer, is Atlas strange? But how strange? Who knows? And when did they know? The geometry of the solar system doesn't lie. The brightness recorded by multiple independent sources can't be fabricated either. The timing of the announcement, compared to the actual observation, cannot be a coincidence. So, what are we being kept from? Later in this journey, you will see orbital diagrams, which explain why the phrase "behind the sun" is sometimes more convenient than accurate. You will see superimposed images from cameras on Mars, frames from coronagraphs, and even amateur images that show an object in the exact place NASA says it is unseen. You will hear about unnatural acceleration theories, about technological footprints, and the possibility that Atlas is using this close approach to do something more than simply evaporating ice. And this is what keeps me up at night. If the independent observers are right, if this object was indeed visible during the period we were told it was impossible, then all the press conferences, all the statements, all the lost sightings are not mistakes. They are choices, and all choices have a reason. So why? We live in an age where citizen scientists can outsmart billion-dollar organizations, where machine learning algorithms spot anomalies before peer review boards, and where a single Reddit post can cause the entire system to review its own data. Astronomy is no longer a privilege, it's a responsibility, but that responsibility comes with risk, because misinterpretation is as easy as observation. So, buckle up. We're going to go deep into the fog of data, through institutional silence, and through the uncomfortable gap between what we're told and what's actually happening. You'll come out of this journey with more questions than answers, but at least you'll know which questions to ask, and you'll know where to look when Atlas reappears, because October 29 is not the end. It's not even matter, the true beginning. Orbital calculations show that perihelion, the point at which the object is closest to the Sun, will fall around October 29 or 30, 2025. At that point, the object will be approximately between 1.36 and 1.4 astronomical units, AU, from the Sunday. In other words, it is farther than Earth's orbit, farther than Mercury or Venus have ever come close. So why the lost track? The answer lies in the observational geometry. From Earth's perspective, as Trisi, Atlas approaches perihelion. It moves into a position where the Sun is almost directly between us and the object, or close enough that the Sun's glare will blind any telescopes trying to observe it. NASA has released its visibility calendar. They say that ground-based telescopes will only be able to observe 3I Atlas through September. Then, a solar conjunction will make it invisible until December, when it reappears on the other side of the Sun and can be seen in the early morning sky. This explanation makes sense if you understand elongation angle. When an object is within 15 to 20 degrees of the Sun, as seen from Earth, the sky becomes so bright that conventional telescopes cannot work. Simply put, you are trying to see a flashlight placed next to a headlamp. That brightness is insurmountable without specialized equipment. And NASA has also made it clear in its technical documents that some special equipment can still pick up its faint light, like solar coronagraphs, which are devices designed to cover the Sun's disk and observe its bright corona. Sometimes, these same devices can detect comets that pass very close to the Sunday. But for the general astronomy community, especially amateur observers using backyard telescopes, NASA's message is clear. October to early December equals the dead period. Don't waste your time looking, because you won't see anything. Previously, the Hubble telescope gathered data in early 2025, which helped estimate the size of the comet nucleus. Measurements showed the object was quite small, just a few kilometers across, but had significant cometary activity. Its speed was recorded at about 60 kilometers per second as it entered, a typical value for interstellar objects not bound by the gravity of the solar system. NASA classifies 3I Atlas as an active comet rather than an inert asteroid based on observations of the gas and dust, surrounding the nucleus. Then came the James Webb Space Telescope's observations in August 2025. The Near-Infrared Spectrometer, NIRSpec, found that the surrounding gas was mostly carbon dioxide, CO2, not water vapor, the primary volatile in most solar system comets. It was the first sign of something unusual, but NASA explained that this was consistent with an object forming in a cold, distant protoplanetary disk where CO2 ice predominated over water ice. Unusual, yes, but not impossible. Scientific papers posted on arxiv.org describe the composition of 3I Atlas as unusual but explainable. In public statements, NASA often uses phrases like "too close to the sun to observe" and "behind the sun" interchangeably. To professional astronomers, the two clusters are practically equivalent. You can't observe because of interference from the sunday. But to the general public, these two expressions conjure different feelings. Behind the sun sounds as if the object is completely obscured. Too close to see sounds more technical, like an instrument limitation. And it is this linguistic difference that matters if you want to know how accurate NASA is or how they are shaping perceptions. From NASA's perspective, there's no cheating. They're just following standard procedure. When an object enters a solar conjunction, they announce the date of the disappearance, warning that the observation window is closing. Then they schedule another observation. When the object reappears, there's no reason to update daily during the disappearance because there's nothing to report. The object is just doing what physics predicts, following a stable orbit, fading out of view due to the angle. The story, it seems, ends there. Except it didn't end, because while NASA was issuing signal loss warnings, independent observers were piecing together images from solar observatories, Mars orbiters, and coronagraphs that were largely unknown to the public. And they saw something, not a void, but light, something bright enough to be observed, moving in a way that did not perfectly match the predicted position, ephemeris, and raising a question that NASA probably did not expect to be asked. If 3I Atlas was supposed to be unobservable, why was it observed? On the 28th of October 2025, a post appeared on a citizen science forum. The user had combined multiple images from the GOES satellite sun tracking platform of the National Oceanic and Atmospheric Administration, NOAA. GOES was not designed to find comets. It observes the sun to detect coronal mass ejections or magnetic storms, but its coronagraph can cover the sun's disk and record the corona, where sometimes is from faint objects appear. This user claims to have spotted an unusual peak consistent with comet activity in the exact location where 3I Atlas is predicted to appear if the orbital elements released by NASA are correct. But NASA says it is not observable, so either the user is wrong or NASA is not telling the whole story. The post includes the shooting time, the stitching method, the alignment data, very detailed and scientific, not just a blurry photo with a red circle around a random bright spot. It's attention-grabbing. Then came the Mars view. On October 3, I Atlas passed relatively close to Mars, enough that some astronomers speculated that its cameras could capture images. Perseverance carries a navigation camera, and Mastcam Z, a high-resolution stereoscopic camera. While these cameras are primarily pointed down at the surface of Mars, they can be steered to observe the sky. And according to at least one independent post, someone claims to have found evidence of 3I Atlas in publicly available photos of Perseverance right around the time of its flyby. Observing from Mars is difficult. Cameras are not optimized for distant, dim targets, short exposure times, narrow fields of view. But Mars has a different perspective from Earth. In early October, since then, 3I Atlas has not yet entered its conjunction phase. That different geometry allows Mars to see what next time Earth cannot. If true, this does not negate NASA's lost track from Earth claim, but merely adds data from another perspective, one that NASA has not emphasized. In its public messaging, amateur astronomy forums began to vibrate. They compared data, composited images, matched timings to orbital predictions. Some claimed they saw faint comet tails in coronagraph data. Others noticed unusual brightness fluctuations, which did not fit the simple rotating nucleus model. Some pointed to jets of material shooting toward the sun instead of away, a phenomenon that is completely contrary to the principle that solar radiation pressure always pushes dust and gas outward. A Medium article argued that 3I Atlas was not behind the sun in any real sense. The author calculated the angle of elongation from various observation sites and concluded that, although Earth was indeed eclipsed, certain specialized instruments, particularly coronagraphs and cameras on Mars, would still be able to observe. Cameras located beyond Earth, particularly those on Mars, should have maintained their ability to observe. And if that were true, then the lost track narrative that NASA published was at least an oversimplification. The question of credibility began to grow larger. Independent observers don't have the same calibration standards, don't have the same peer review system, and don't have the institutional backing of NASA. Their images may contain noise from frame overlap, hot pixels, cosmic ray collisions, or subtle alignment errors. Image processing can introduce bias, and sometimes their conclusions stray too far from the actual data. But the pattern repeats. Multiple sources, multiple instruments, multiple people, all detecting something in the exact location that NASA said nothing could be seen. Then came the brightness reports. Several independent observers claimed that 3I Atlas was brighter than expected during the conjunction. Comet brightness usually follows a power law based on distance from the sun and distance from Earth. If you know its size, activity, and orbit, you can predict its brightness at any given time. But if these independent observations are correct, 3I Atlas has exceeded all expectations. It's brighter than the model predicts, which means the nucleus is more active, or the dust output is higher, or something else is going on. What's important here is not just the data, but the sentiment framed. This is the democratization of observation in astronomy. People not waiting for NASA to analyze data, downloading public coronagraph frames, scanning the Mars rover's data repositories, and sharing files on Discord and Reddit. They're not trying to undermine NASA. They're just trying to see what's really going on. And what they see doesn't match what they're told they'll see. Now there are two parallel stories. NASA says the object is in the phase of disappearance, cannot be observed. Wait until December to observe again. And independent observers say the object is still present, can be observed with other instruments, and its behavior is unusual. Who is right? And if both are partly right, what does that mean for trust, transparency, and how we handle unprecedented observations? Because if independent people can uncover what official channels ignore or deliberately de-emphasize, the gatekeeper role of large organizations begins to erode. That could be a healthy step or the beginning of chaos, but it is happening. Now let's talk about what makes 3I Atlas truly strange beyond any observational debate. Even accepting NASA's original data and setting aside amateur debate, this object still exhibits behaviors that are outside the normal cometary norm. And when you combine that behavior with the controversial observations, you understand why many people are starting to ask uncomfortable questions. First is the predominance of carbon dioxide. The James Webb Space Telescope found that the gas surrounding the object was predominantly CO2 rather than water vapor. The primary volatile in most solar system comets, CO2, is typically dominant only in extremely cold formation environments or in objects whose water ices have been stripped away by the sun over multiple perihelions. But 3I Atlas was an interstellar visitor, almost a first-time visitor to the solar system, so it could not have been eroded by the sun before. The predominance of CO2 suggests that it formed in an environment that was much colder or had a significantly different chemistry than the comet-forming regions in our solar system. Then there is the phenomenon of polarization. A paper on rxiv.org describes that light reflected from 3I Atlas shows extreme negative polarization. Polarization measures the direction in which light waves oscillate. As light scatters through dust, the polarization depends on the size, shape, and composition of the dust grains. Extreme negative polarization suggests either the dust has very unusual properties, or the dust grains are very small, or the grain size distribution is unlike any known comet. The paper does not say it is artificial, just notes anomalous and needs further study. Next are independent reports of the direction of the jets. Comets spew gas and dust when subsurface ice evaporates from the sun's heat. Normally, these jets point away from the sun because radiation pressure pushes the material outward. But many people say they see jets pointing in the opposite direction, toward the Sunday. If that's true, either rotational effects cause the jets to sweep forward, or there's an active mechanism to push material out, overcoming radiation pressure. And then there are the unusual brightness spikes. Comets can flare up when a new pocket of ice is exposed or a fragment of the nucleus breaks, increasing the area of activity. But independent reports show that the brightness spikes are much stronger than the natural evaporation model can explain. And then some reports came back with timestamps right in the conjunction window, the time when NASA claimed the object was invisible. So either the spikes happened earlier and observers got the date wrong, or they actually happened during the conjunction, right when no one should have seen anything. Next, there's the story of the orbit. 3 Atlas is on a hyperbolic orbit, which means it is not held back by the Sunday. With nothing else at play, gravity alone will determine its path. unless something non-gravitational intervenes. With comets, that thing is usually outgassing. When material is ejected from one side of the nucleus, it gives a small kick, enough to deflect it. This phenomenon is called non-gravitational acceleration. It is well documented in active comets, but the magnitude and direction of this force depends on the jet and the rate of mass loss. If 3I Atlas is ejecting material in unusual directions, or if its brightness indicates a higher mass loss rate than expected, then the orbit may be slightly off from the purely gravitational model. However, no one has yet recorded a definitive deviation. The fine-tuning of the orbital elements is still ongoing, but if future observations, especially after its re-entry in December, show 3 Atlas is no longer on track, that would be a significant sign. It could mean that the outgassing model is wrong, or that something else is controlling its movements. And from there, speculation begins to creep in. What if this isn't just a gas outflow? What if the jets are controlled, timed, pulsated in a deliberate pattern? What if this object is using its close approach as an Oberth springboard, where the engine is fired up at the exact moment of maximum speed, closest to the sun, to maximize the energy gain? A bold scenario, a bit reckless, but it starts to sound not so implausible when you put all the strange signs together. Avi Loeb, the Harvard astronomer who has argued that Oumuamua could be artificial, has raised the possibility that such interstellar visitors could be probes or remnants of other civilizations. He calls it the Loeb scale, a system for assessing the likelihood of technological traces. 3I Atlas has never been formally scored on this scale, but if we were to apply it, we would consider deviations from natural motion, unusual chemical composition, controlled orientation, and non-random variations in brightness. Alone, these signs are inconclusive. But when they are put together, the story begins to change. The comforting truth is, we still don't have enough data to rule out any of these hypotheses. Professional observations still show a natural, but somewhat anomalous comet. Independent observations, if accurate, add details that nature probably could not have produced on its own. So, any hypotheses about artificial behavior are still speculative at this point, but the window for outright rejection of those scenarios is narrowing. If 3I Atlas again breaks predictions on re-emergence, if it deviates significantly from its trajectory, if the outgassing models fail to explain it, then the story moves on to another chapter, and the agencies who have been saying for months that it's just a comet will be forced to speak up. Part 5. Breaking the official silence. Timelines. Communication patterns. Let's take a look back in time, see who said what and when. The 1st of July 2025, NASA announces the discovery. A short, cold scientific bulletin. An interstellar object, a hyperbolic orbit, a perihelion expected in late October. The tone is restrained. Interesting, but not new. We've seen interstellar objects before. August. James Webb Space Telescope detects CO2-dominated spectrum. Data released. Papers appear on arXiv.org. NASA's familiar choice of words. Unusual instead of unusual. Further study instead of unexplainable. Neutral language, enough to reassure the public, but enough for researchers to understand something is strange. September. Ground observations continue. comet brightens, light polarization becomes strange. NASA warns that conjunction is approaching and the object will soon be unobservable. That phrase, too close to the sun for ground telescopes, is accurate, but it doesn't say it all because it ignores other observing platforms. October 3. 3 Atlas passes Mars. No announcement, no photos, no confirmation that Perseverance has tried to point its camera at the sky. A notable silence. Maybe the rover didn't take the photos, or the images weren't processed, or the data wasn't solid enough. But either way, silence always creates a void, and the void is always filled with speculation. October 15 to 25. Pre-perihelion acceleration phase. NASA remains silent. No press conference, no blog updates. Not a single new entry on NASA Science. Last update. Meanwhile, independent observers posted frame after frame of coronagraph overlap, reported anomalies, and the question kept repeating, why are we still seeing what NASA says is invisible? And NASA still said nothing. October 29 update. The day that, as predicted, 3I Atlas disappeared. Instead, independent observers say they saw it brighter than ever, most active, most noticeable, most obvious, through instruments that NASA said were invisible. No response, no correction, no explanation, just silence. Entering November, the object is moving away from the Sunday, still in conjunction, still out of range of ground-based telescopes. Official NASA channels are as quiet as a starless sky. A brief update appeared on NASA Science, reiterating that the re-entry window would open in December. No mention of independent observations, no mention of coronagraph data, no mention of images from Mars. Nothing. Compared to how they handled Oumuamua in 2017-2018, this silence is strange. Back then, NASA and ESA talked openly. They argued, explained, and released data quickly. Not perfect, but transparent. This time, transparency seems to have worn thin. NASA finally spoke up, but only after public pressure mounted. 2. I. Borisov, the second interstellar visitor, was clearly a comet and was hardly controversial. NASA was straightforward, transparent, understandable. 3 I Atlas, the third visitor, hovered between two worlds, as mysterious as Oumuamua and as unassuming as Borisov. NASA's response was different, restrained to the point of being almost opaque. The question is that restraint prudent or is it control? Are they being careful not to overstate when the data is still missing pieces? Or are they shaping the narrative, setting boundaries for who sees how much until they decide? What is the official version? Because in a world where citizen scientists can pull frames from a coronagraph, process them, and post them online in a matter of hours, keeping the narrative is no longer the prerogative of large institutions. And perhaps that is what we are witnessing. It's not a conspiracy, nor a cover-up. It's just an old system struggling to adapt to a new world where the public doesn't wait for a permit to observe and interpret the sky. December will be the test. When 3I Atlas returns, when professional telescopes can observe cleanly again, we'll know whether the anomalies persist and whether NASA's predictions still hold. We will see then whether the independent observers are vindicated or are chasing noise and illusions. Until then, the silence is louder than any press release. Now, let's get a little technical, because observational geometry is the key to knowing who's right and who's looking in the wrong direction. When NASA says an object is behind the sun, they are using a shorthand for the observation limit called solar elongation. Elongation is the angle between the object and the sun when viewed from a given location, usually Earth. When this angle is small, say below Ishipshamshipgud, the sunlight overwhelms everything. Imagine trying to see a firefly flying right next to a stadium floodlight. The firefly is still there. It still glows, but the headlights are so bright that your eyes can't separate it from the background light. That's a solar conjunction. When the object doesn't disappear, it just becomes invisible to conventional instruments. But not all instruments are conventional. Coronagraphs are specially designed to cover the sun's disk and observe the surrounding corona. They use a physical occulting disk to block direct light, allowing the fainter light of the corona and foreground and background objects to be captured. Satellites like SOHO, Solar and Heliospheric Observatory, carrying coronagraphs, have repeatedly spotted comets passing close to the sun, sometimes just a few solar radii away. 3 Atlas is much farther away per astronomical unit, but still within the field of view that the coronagraph can cover. So, when independent observers say they have spotted 3 Atlas, in coronagraph data, they are not breaking the laws of physics. They are simply using the right instrument that was designed to overcome the sun's corona. NASA is not lying when it says that ground-based telescopes cannot see it. They are just not emphasizing that some other instruments can. Now, let's add Mars to the picture. Mars orbits the sun at a different position and distance from Earth. In early October 2025, the 2 planets will not have the same line of sight configuration. From Mars, 3I Atlas may have a larger elongation angle, meaning less solar interference. The Perseverance rover and the Mars orbiters both carry cameras that can take pictures of the sky. They are not optimized for hunting dim light sources, but under the right conditions, they can still capture comets, asteroids, even distant galaxies. And the October 3 Mars flyby opens a rare opportunity that those cameras might have seen something if someone on the control team had instructed Perseverance to point up in the right sky with the right exposure settings. It would have likely captured 3 Atlas before the object entered conjunction from Earth's perspective. And if those images exist, they would show the object at a time when NASA had begun communicating its loss of visibility. Not that NASA is lying, but because they are talking specifically about visibility from Earth. Equipment sensitivity also plays a role. The brightness limit, the dimmest the telescope can detect, depends on aperture, exposure time, background noise, and pixel pitch. Professional observatories can push the field of view to extremely faint stars. Amateur telescopes cannot, but stacking, combining dozens or even hundreds of frames, helps them pull the faint signal out of the noise and dig deeper than is normally possible. If independent observers stacked hundreds of coronagraph frames, they could definitely pull out a real signal, which in a single frame you would never see. Of course, calibration is always a fine line. Professional telescopes have inaccuracies, atmospheric extinction coefficients, well-measured systematic biases. Amateur stacks are not so tight. A bright peak in an amateur photo may be real or just a hot spot, cosmic rays, or a satellite streak. Without knowing the processing, it is difficult to judge. But one thing is worth noting. Many people, many devices, many methods, and even different software all report the same phenomenon. That repetition suggests that the prevented channel 10 signal is real and not random. Of course, it is still possible that they were wrong in the same way, but that probability is much lower than the other possibility that they were actually seeing a real object, which NASA's public messaging has downplayed, because the phrase "behind the sun" sounds definitive, as if the object has disappeared from the universe. But in astronomical reality, that is rarely absolutely true. Objects in conjunction are indeed harder to observe, very hard. But hard is never synonymous with impossible. And when NASA uses language that suggests impossibility, they leave themselves vulnerable to accusations of misleading when alternative observations emerge. Now for the imaginary diagram. Imagine the sun at the center. The Earth rotates at a distance of 1 AU. 3I Atlas enters from interstellar space, hurtling toward the sun, reaching perihelion at 1.4 AU. As it gets closer, the angle between Earth, the sun, and the 3I Atlas gets smaller. When elongation falls below a certain threshold, Earth-based telescopes lose their ability to observe, but Mars, orbiting at 8,5 AU and in a different orbital phase, has a different angle. From Mars, the elongation may still be large enough to observe. Similarly, a coronagraph in near-Earth space can see through the sun's corona to regions that ground-based telescopes cannot reach. NASA's message focuses on the Earth-based view because most observers are here, but by not making it clear that other platforms could still remain visible, they created the impression of a complete blackout. And when independent observers used alternative data sources to report their findings, it made it look like NASA was hiding the possibility. The scattering angle is also important. The light reflected from the comet dust scatters in specific patterns, depending on the phase angle. The angle between the sun, the object, and the observer. At certain phase angles, the scattering efficiency increases, making the object brighter than would be predicted from distance alone. If 3I Atlas falls into favorable scattering geometry during a conjunction, it may appear brighter in the coronagraph than the inverse square distance calculation. That could explain some reports of brightening without invoking anomalous activity. But noise is also part of the story. Cosmic rays, sensor saturation, the blooming effect of bright nearby light sources, and background noise. Professional astronomers spend their careers distinguishing signals from artifacts. Amateurs often lack that training, but make up for it with enthusiasm, independent repetition, and community validation. When a detection is repeated by multiple users, multiple devices, multiple processing procedures, confidence increases, even if individual frames are still noisy. The key takeaway is, behind the sun is an observational shorthand, not an absolute truth. Geometry limits visibility, but does not eliminate it. For all instruments and all platforms, NASA's framing is accurate in a narrow context, standard Earth-based optics, but incomplete when viewed across the entire observational ecosystem, and that incompleteness leaves room for independent observers to fill in, and for skepticism to take root. If geometry allows for alternative observations, which it clearly does, then why isn't NASA's public messaging more explicit? Is it an oversight or a choice of discursive framing to manage public attention? Whatever the answer, it impacts trust, hypotheses beyond normal outgassing. We enter the realm of speculation. Let's be clear from the start. There is no definitive evidence that 3I Atlas is artificial. No, all observations so far can be explained with varying degrees of comfort by natural cometary processes, but the accumulation of strangeness, the CO2 dominance, the extreme polarization, the controversial brightness of the conjunction, the allegations about the jet direction raises the question that science must ask. Though the answer is hard to believe, what if this is more than just a comet? Loeb has spent years arguing that we should take seriously the possibility that the interstellar visitor is a probe or an artifact of another civilization. His analysis of Oumuamua suggests it could be a light sail, a thin, reflective structure accelerated by solar radiation pressure. The scientific community has largely rejected that interpretation in favor of natural explanations like escaping hydrogen gas or nitrogen ice. But Loeb's broader point still stands. If we are looking for extraterrestrial intelligence, we must look not just for radio signals, but also for physical objects, probes, drifting bodies, anything that exhibits behavior incompatible with natural processes. He proposed an informal framework called the Loeb scale for grading technosignatures in observable objects. The scale considers deviations from predicted motion, unusual material composition, geometric regularities, controlled orientation, and non-random behavior. 3I Atlas has not been formally rated on this scale, but let's go through each criterion. Deviation from predicted motion. To date, no confirmed measurements have shown that 3I Atlas deviates from its predicted gravitational orbit beyond what can be explained by outgassing. Keyword: to date. If observations following the December conjunction show orbital deviations that cannot be attributed to the measured outgassing, that would be a significant sign. The non-gravitational acceleration of the comet is proportional to the mass loss. If the motion requires more thrust than what the observed dust gas provides, you will have a mismatch that needs explaining. Unusual material composition. Yes, CO2 dominance is strange, but not impossible. It suggests formation in an extremely cold environment, colder than the solar system's cometary birthplace. That could indicate an origin in a low metallicity star system formed from primordial gas with fewer heavy elements. Or it could be that the object wandered for billions of years in interstellar space that was cold enough to hold on to CO2 while losing its lighter components. Natural solutions exist, but require rare conditions. Geometric regularity. We don't have high-resolution images of the nucleus yet. Hubble constrains the size, but not the shape. If future observations show elongated structures or flat surfaces, too normal to be due to natural erosion, that would raise a flag. Oumuamua was once estimated to have an axial ratio of is approximately equal to 10:1, unusual, but not impossible. If 3I Atlas shows similar or more extreme geometry, the artifact hypothesis would increase in likelihood. Controlled orientation. Controversial reports of sun-directed jets are here. If the jets are real and directed to produce thrust in a particular direction, that could be an indication of control. But jet direction can vary naturally with rotation and the distribution of active regions across the nucleus. You need to prove that the orientation is non-random, persistent in a way that produces a net acceleration in a preferred direction. This is difficult without continuous monitoring, which we don't have in conjunctions. Non-random behavior, hardest to assess. Random or intentional requires statistical analysis over time. A single peak is just one event. Multiple peaks that repeat regularly or correlate with certain orbital positions begin to resemble a pattern. If 3I Atlas were to exhibit rhythmic flickering activity, uncorrelated with solar heating or rotation, that would be unusual. But right now, we don't have that data. So how does 3I Atlas score on the lobe scale? Probably low to medium. It has some strange properties, but nothing that definitively rules out natural processes. For now, it's worth watching closely, not definitely artificial. However, that score could change as new data emerges. Imagine a scenario. Suppose 3I Atlas is the object being designed, a probe from another civilization. What is it doing here? One possibility is the Oberth maneuver, a technique of burning or ejecting mass at the highest velocity point and near the most massive body to maximize energy. For spacecraft, performing an Oberth near the Sun combines gravitational flapping with active thrust, allowing for large orbital changes with little fuel. If 3I Atlas uses perihelion to harvest energy from the Sun, thermal or photovoltaic conversion, and then ejects material to correct its orbit, that could explain reports of unusual jets. The Sun-directing jets could be attitude control micro-engines, rotating the object to maximize energy capture, or aligning it for the next mission phase. Conjecture, yes. Impossible, no. Another scenario, passive surveillance. Maybe the object isn't moving at all. Maybe it's an ancient wreck, long out of control, but still has residual activity from decaying systems. The bright peaks could be flashes of power from malfunctioning equipment. The strange components could be decaying composites. The trajectory could be the traces of a maneuver performed long ago, and now we're just seeing an inertial object passing by. Or maybe it's still active and deliberately avoiding detection. If an advanced civilization wants to study the solar system without revealing itself, they could design a probe that disguises a comet. They use exhaust to mask engine activity, keep the orbit looking purely gravitational. Time maneuvers at solar conjunctions, knowing that any anomalies will be attributed to noise or dismissed as amateur misunderstandings. The latter scenario sounds vaguely conspiracy theory, but it's not unreasonable. If we were designing an interstellar spacecraft, we would also minimize the observational footprint. We want data, but not interference. We would use a natural shell, and if the spacecraft is detected, we hope the host civilization will assume it is natural, unless the evidence becomes overwhelming. The problem with all of these scenarios is that they attribute intention when there is no evidence of intention. All of the 3I Atlas observations can be explained by natural processes, even if those explanations require strange but possible conditions. CO2 dominance, explained by an extremely cold formation environment. Polarization, explained by unusual dust properties. Conjunction brightness, explained by favorable scattering geometry or processing artifacts. Jets, explained by rotation and surface inhomogeneity. You don't need artificial intelligence. You just need a strange but natural comet. Occam's razor favors the natural solution. The simplest hypothesis that fits the data is usually correct. But Occam's razor is just a heuristic, not a law. Sometimes reality is complicated. Sometimes the simple solution is wrong. And for interstellar visitors, our sample size is only 3. Oumuamua is strange enough to spark serious debate about its artificiality. Borisov looks like a normal comet. 3I Atlas is somewhere in between. Strange enough to be interesting, but not strange enough to be conclusive. The honest answer is, we don't know, and we won't know until more data comes in. The way to get more data is to keep observing, keep measuring, and keep asking these uncomfortable questions. Because if 3 Atlas is natural, understanding its strangeness will teach us about the diversity of objects in the galaxy. If it is artificial, that changes everything. Just one confirmed technological trace, an object that cannot be explained by natural processes, will prove we are not alone. It will validate decades of SETI research. It will reframe humanity's place in the universe. So we observe, we wait, we resist the temptation to jump to conclusions. We maintain a tension between skepticism and openness. We demand evidence, but do not dismiss possibilities just because they make us uncomfortable. The universe is not obliged to make sense to us, and sometimes extraordinary discoveries start from the exact same anomalous data point that everyone else has overlooked. Zoom out. 3I Atlas is just one object, but it is part of a larger conversation about how scientific institutions communicate with the public, how they manage uncertainty, and how they respond when outsiders challenge their narrative. This conversation is not new. It has been building for years, perhaps decades, as the democratization of information collided with the traditional gatekeeping role of experts. Remember Oumuamua, October Landshandling Yishuti, the first confirmed interstellar visitor, elongated, wobbly, accelerating away from the sun in a way that cannot be explained by gravity alone. The scientific community has offered several natural explanations, outgassing from evaporated ice, though no coma was seen. A chunk of hydrogen ice, though hydrogen ice is unlikely to survive in interstellar space. A piece of nitrogen ice from a Pluto-like planet, though the chances of such a piece entering the solar system are extremely small. Avi Loeb suggests it could be man-made, a light sail or fragment of it. The reaction from the astronomical community was swift and largely negative. Loeb was accused of attention-seeking, damaging the credibility of science, hastily calling out aliens. But he countered, we should be open to all possibilities, rejecting the pre-existing artificial hypothesis is also unscientific. Debates took place in magazines, conferences, spread to the media. The public watched with fascination as scientists argued about what sounded like science fiction. NASA's role at the time was quite modest. They didn't support Loeb's theory, but they didn't completely shut it down either. They released the data, encouraging further observations, even though Oumuamua was too far away to track. They acknowledged the anomalies, while still favoring a natural explanation, a balancing act, maintaining credibility, without appearing closed-minded. Now, compared to 3I Atlas, the anomalies are less dramatic than Oumuamua, but still present. Public interest is growing. The independent observers are better organized, more vocal. NASA's response has been more muted. Fewer announcements, less interaction with alternative claims, more of a wait-and-see strategy. Is this because the data are less compelling, or because they learned from Oumuamua that engaging in debate will raise more questions than answers? There is a tension between scientific caution and public transparency. Scientists are trained to wait for peer review, avoid over-interpreting preliminary data, and hedge in uncertainty. But the public wants answers now. They want to know what is going on in their skies. They don't want to wait 6 months for a paper to pass peer review. And when institutions prioritize caution over communication, the gap is filled with speculation, some plausible, some not. The phrase, "behind the sun," is a case study of how discursive frames shape perceptions. 2. Astronomers, it is jargon for a solar conjunction that makes it difficult to observe. To the public, it sounds like the object is hidden and we can't talk about it. NASA most likely did not intend to create the latter interpretation, but that is what many people heard. And when independent observers posted photos claiming to have seen the object during the cloaking phase, it made NASA appear to be caught in a frame shift between narrative and reality. Was it intentional misdirection? Most likely not. More likely, it was a communication choice that prioritized simplicity over accuracy. NASA wanted to tell the public, "You won't see it for the next few months, so don't bother." They used plain language to convey that message. They didn't anticipate that someone would interpret "you won't see it" as "no one will see it," or that alternative observing platforms would produce data that contradicted the simplified story. But in the era of citizen science, such simplifications become a weakness because there will always be people checking, pulling coronagraph data, stacking frames, comparing timestamps, and if what they find doesn't match what they're told, trust will erode. This isn't unique to NASA. This is a broader challenge for all scientific institutions. How do you communicate complex, uncertain information to a public hungry for clarity? How do you maintain authority when anyone with internet access can access the raw data and draw their own conclusions? How to respond to challenges from outsiders who have no formal training, but sometimes see what the experts miss? Some institutions respond by doubling down on gatekeeping. Only peer-reviewed findings are considered valid. Only credentialed scientists can make authoritative claims. Amateur contributions are welcome, but must be formally reviewed. Such an approach preserves credibility, but risks alienating the very people who could be valuable collaborators. Others choose openness. They release data quickly. They openly discuss amateur findings. They acknowledge uncertainty and invite scrutiny. This approach builds trust, but it can easily lead to a deluge of claims, many of which are false or misleading. NASA tries to walk a fine line between the two extremes. They publish their data in public repositories. They attend forums and conferences where amateurs present their findings, but they maintain standards. What counts as confirmation, what makes it into the mainstream media, and sometimes the middle path doesn't please anyone. Professionals feel they have been too lenient with amateur speculation. Amateurs feel they have been overlooked. 3. Atlas may force everyone to recalibrate. If the independent observer's claims are vindicated, if December observations confirm the anomaly is real, and the replacement instruments are indeed still visible during the conjunction, NASA will have to answer. Why didn't it communicate those possibilities more clearly? They will be accused of oversimplification at the very least, of narrative control at the very most. And if the independent claims turn out to be false or misinterpreted, NASA will still be asked why it did not proactively engage in further clarification. Staying silent in the face of mounting speculation can easily make them appear dismissive or evasive, though sometimes it is just patience. There is a layer of philosophy here too. Who owns the sky? Who has the right to interpret what is observed? In some ways, the sky belongs to everyone. Anyone can look up, point a telescope, analyze the data, but interpretation requires expertise, context, systematic errors, calibration, and the limitations of the instrument. So should only experts speak in public? Or do we need a new framework to integrate amateur contributions into professional discourse? The 3 Atlas will not answer definitively, but it is a data point in the evolution of how science communicates with society, and the outcome will shape how we handle future anomalies, the next interstellar visitors, the next discoveries, because the next time something strange appears, and it will, both institutions and individuals will remember what worked and what didn't. They will adjust. Hopefully, we move towards a model where transparency and rigor coexist, where amateurs and professionals collaborate rather than clash, where the public trusts that they are getting the full picture, even if that picture remains uncertain. While NASA remains silent, the internet did what it always does: mobilize. Within days of the first posts, from independent observers claiming to have seen the conjunction, astronomy forums erupted. Reddit threads on our space, our astronomy, even our conspiracy began tracking 3 Atlas. Citizen astronomer Discord servers shared raw data files. Users compared notes, cross-referenced orbital elements, debated processing methods. One prominent post describes an attempt to stack GOES coronagraph frames. They downloaded hundreds of images covering the perihelion window, aligned them to star positions, denoised them, and looked for a consistent signal across frames. The result was a faint but detectable increase in brightness at the expected location of 3 Atlas. Users posted the entire method, software settings, source files. Others tried to replicate it. Some succeeded. Some saw only noise. The debate turned into a collective verification effort. Another user focused on Mars. They scanned the Perseverance rover's public image archive, looking for frames of the sky taken during the early October flyby. Most of the images were surface geology, rocks, sand, distant mountains, but there were a few frames pointing skyward, which could have been calibration or navigation test frames. In those images, after heavy enhancement, the user claimed to see a blur, consistent with a fast-moving object. They calculated the expected position using the published orbital element. The match was close, but not perfect. Close enough to be interesting, but not enough to be certain. The strengths of the community effort are clear. Repeatability, many people, many ways, reaching the same conclusions. Transparency, open data and methods, inviting scrutiny and replication. Speed, posts appear within days of perihelion, faster than any peer review. And diversity, from retired engineers, seasoned amateur astronomers, programmers, students, all over the world contributing their perspectives. But the weaknesses are also evident. Calibration uncertainty. Amateur image processing does not always take systematic errors into account. A bright pixel may be a signal, but it may also be an unmasked hotspot. Confirmation bias. When looking for anomalies, it is easy to interpret ambiguous data in a way that supports it. Sampling bias. Dozens of people who see nothing may stay silent. Only those who see something post. Ambiguity in timestamps is also a problem. Spaceborne data has time metadata, but it is not always easy to read. UTC versus local time, or ship time, can be confusing, off by a few hours. A detection claim during a conjunction may actually be before or after the key window. Frame alignment is also not simple, off by just a pixel or two. The superimposition can create an illusion. It looks like the blurry object is moving. Professionals use sophisticated alignment algorithms compared to known star positions. Amateurs often use simpler tools, which are effective in most cases but prone to errors at the edges. Still, the community effort has value. It acts as a decentralized verification network. It can catch things that slip through the institutional loop. It raises questions that experts sometimes don't think about. And it creates a public record which persists even when the official channel goes silent. One group even tried to standardize the process. They created a shared spreadsheet, logging the tests, date, device, method of processing, and results. The goal is to collect enough tests to judge whether the signal is real or the result of a process prone to false positives. As of early November, the table had over 50 entries. About 30 reported positive detections, 20 reported false positives or no detections, a success rate of 60%, suggestive but not definitive. The negative results are also important. They show that detecting 3I Atlas during the conjunction is no mean feat. It requires good data or good processing, or both. If everyone who tries sees it, the claim is stronger. If only a few people see it, they may have gotten lucky with a false positive. The 60% reality lies somewhere in the gray area between those two possibilities. Some members of the community began pushing for an official release of the data. They filed a Freedom of Information Act request, asking for any images from Mars orbiters of 3 Atlas. They contacted NASA's Planetary Data System to ask about the Mars Reconnaissance Orbiter's observation schedule in early October. They messaged the SOHO science team, asking if the coronagraph data had seen the object and when it would be made public. The response was mixed. PDS confirmed that Perseverance's images were publicly available, but noted that not all images were processed immediately. Sky calibration frames can take months. The SOHO team confirmed that the coronagraph data was public and archived, but cautioned that interpreting the faint signal in the sun image required expertise. They neither confirmed nor denied whether 3 Atlas appeared in the data. NASA's silence on these requests is not necessarily suspicious. Large organizations have bureaucratic processes. Requesting data takes time. Confirming or denying a faint signal requires analysis that cannot be done in a few days. But from the community's perspective, the silence looks stubborn. They have images they believe to be objects. They want official confirmation or denial, but have not received either. This contrast between community urgency and institutional caution is shaping the face of modern citizen science. The community wants to contribute. They want to be taken seriously. They want their findings incorporated into the professional narrative. But sometimes they overestimate the certainty of their conclusions, underestimate the complexity of their verification, and assume that because they see something, it must be real, without considering all the ways in which equipment and processing can be misleading. For their part, professional astronomers sometimes underestimate the competence and thoroughness of amateurs. They assume amateur data are of poor quality. Amateur conclusions are hasty. They do not always receive amateur findings promptly or respectfully, and this creates frustration, a sense that institutions are gatekeeping knowledge rather than collaborating to expand it. The ideal outcome would be a partnership. Amateurs discover and flag interesting signals. Professionals track with high-quality equipment and rigorous analysis. Discoveries are published collaboratively. Credit is shared. This has happened many times. Supernova discoveries, asteroids, variablist star tracking have all benefited from amateur contributions. But when the subject is controversial, when the price is the possibility of changing entire paradigms, like an artificial interstellar object, collaboration breaks down. Professionals become defensive, amateurs become aggressive, and the data, the observations that should be at the center, get lost in the noise. 3. Atlas could be the turning point. If the community-generated data holds up, if the December observations confirm what independents say were seen during the conjunction, then institutions will have to admit that distributed verification networks work, that citizen science isn't just a hobby, that sometimes outsiders see what insiders miss, and that might lead to better frameworks for integrating amateur contributions, faster data releases, more transparency. It might not. If community claims turn out to be spurious, if professional monitoring finds no anomalies, the lessons will be different. That verification is hard, that expertise matters, that seeing is not always believing. Whichever way, the effort is valuable, because asking questions, even when the answers are uncertain, is how science moves forward. December is key. According to NASA's timeline, 3. Atlas will be visible again in early to mid-December as it moves away from the Sun and its elongation angle increases. Ground-based telescopes in the southern hemisphere will have the best initial views. The object will appear in the sky before dawn, low near the horizon, then climb higher as the day goes on. Professional observatories have submitted requests for observations. Hubble is scheduled to take further shots, trying to resolve the nucleus and measure any changes in size or activity from the pre-conjunction period. James Webb could be offered another slot, depending on priorities and opportunity objectives. Ground facilities, like the Very Large Telescope in Chile and the Hawaiian site, have expressed interest as long as the object is bright enough and in a good location. The science objectives are clear. First, Confirm the orbit. Is 3I Atlas on track? Or is there a deviation, even small ones, of fractions of a degree, or slight velocity changes will be significant? They will indicate non-gravitational forces, either from outgassing or, in a more speculative scenario, due to active maneuvering. Precise positioning, measurement of the object's position against the star, will be key. Second, characterize the activity. Is the comet still producing coma? Is the dust production rate increasing, decreasing, or staying the same? Are there new jets, or are old jets changing direction? Spectroscopy will show what material is being released. If CO2 continues to dominate, that supports the hypothesis of deep cold formation. If the vapor appears suddenly, it may be a sign that the underlying layers are being exposed as the outer layers erode. Third, monitor the brightness. Comets usually get brighter as they get closer to the sun and dimmer as they move away, following a predictable power law. If 3I Atlas deviates from that curve, suddenly brightens more than expected, or fades unusually quickly, we will need to find out. Photometers track brightness over time, build light curves, and compare them to models. Fourth, look for signs of fragmentation. Comets sometimes break up when they approach the sun, due to thermal shock or tidal forces. If 3I Atlas breaks up near perihelion, we will see many components, separate from the main nucleus. That could explain some brightness anomalies, the spikes caused by freshly exposed ice. The image will look for debris. Fifth, refine the composition. Beyond CO2 and H2O, what else? Methane, ammonia, organic compounds, silicates, metals. Each element or molecule tells a story about where and how the object formed. Multi-wavelength spectral surveys will build a comprehensive inventory. Amateurs have a role too. Garden glasses cannot match professional resolution or sensitivity, but can monitor brightness continuously, catching short-term variations that professional observing schedules might miss. Amateurs can alert professionals of sudden flares or strange changes, triggering targets of opportunity. They also provide repeatability, multiple independent measurements, to confirm that the detection is not an artifact of the device. What should we expect? Several possibilities, ranging from harmless to paradigm shift. On the harmless side, 3I Atlas reappeared. As predicted, orbit matched. Brightness followed the expectation curve. Activity consistent with standard cometary outgassing. Conjunction anomalies explained by artifacts or observational geometric effects. NASA's story vindicated. Independent observers admitted they had misinterpreted noisy data. On the more interesting side, aberrations appear. Orbits are slightly off, requiring non-gravitational acceleration. Beyond the observed outgassing, brightness is higher or lower than expected, suggesting a change in activity during perihelion that is not observed. New jets appear, or old jets change direction in ways that do not correlate simply to quired with rotation period. Compositions reveal unexpected elements or ratios that challenge the formation model. Such findings do not prove artifactual but deepen the mystery, justifying the investment of attention and resources to monitor. On the extreme side, there is something truly bizarre. The object did not reappear where predicted, implying a significant orbital change. The luminosity shows rhythmic behavior, repeating at regular intervals, inconsistent with heating or rotation. The spectroscopy reveals signs of mismatch with natural materials, possibly narrow emission lines, suggesting refined elements or isotope ratios, inconsistent with stellar nucleosynthesis. High-resolution images reveal geometric structures, surfaces with flat surfaces, or regular patterns. Such findings would push 3I Atlas into the realm of potential technosignatures, requiring thorough investigation and follow-up. The most likely scenario lies somewhere between harmless and interesting. Some anomalies will persist, others will be resolved. The scientific community will debate the interpretation. There will be articles supporting both the natural and the paranormal explanations. The public will remain divided between those who believe NASA is hiding something and those who believe the whole story is just a flurry of activity for nothing. And 3I Atlas will continue its journey out of the solar system, fading and eventually becoming too faint for even the largest telescopes to keep up. But here's the kicker: we still don't know. December is a few weeks away. Observations haven't been made. Data haven't been analyzed. Right now, 3I Atlas exists in a state of superposition, both a normal comet and a possible artifact. This is both a vindication and an embarrassment for NASA. It is both a confirmation and a refutation of the claims of independent observers, and we will not collapse that superposition until the measurements come in. So we wait, we prepare, we discuss, we speculate responsibly. We remind ourselves that extraordinary claims require extraordinary evidence, and that the no-effect hypothesis, the natural, boring solution, is often correct. But we also remind ourselves that the universe has surprised us. Sometimes the boring solution is wrong. Sometimes what people dismiss as noise turns out to be a signal. And the only way to know is to keep observing, keep measuring, keep wondering if what we are seeing is what we think we are seeing. December will reveal not just about 3I Atlas, but about how science handles uncertainty, how institutions and citizen scientists cooperate or clash, how humans respond when something in the sky doesn't quite make sense. The object itself is fascinating, but the process, how we grapple with the unknown, may be even more important. Because 3I Atlas is just one visitor, there will be others. And how we handle this one will set the precedent for all the others. While 3I Atlas dominates the interstellar visitor conversation, James Webb is busy rewriting other chapters of astronomy. In September 2025, Webb released data on an exoplanet's atmosphere in a way no one expected. The planet, designated K218b, orbits a red dwarf star about 120 light-years away. It lies in the habitable zone, where liquid water can exist on the surface. Previous observations from Hubble and others had detected water vapor in the atmosphere. Exciting, but not shocking. Webb went deeper. Its near-infrared spectrometer detected not just water vapor, but also dimethyl sulfide, DMS, a molecule on Earth that is produced almost exclusively by biological processes, specifically marine phytoplankton. Finding it in an exoplanet atmosphere immediately raised questions. Is this a trace of life? Does K218b have life? The scientific community responded cautiously. Dimethyl sulfide can also be produced abiotically through photochemical reactions involving sulfur compounds and methane. This detection is close to the Webb sensitivity threshold, requiring careful analysis to rule out instrument artifacts or interference from other molecules with similar spectral signatures. Many groups have jumped into modeling whether non-biological chemistry can explain the observations. Some say yes, possibly through anomalous atmospheric reactions. Others say the abundances are difficult to explain without biology. The parallels with 3I Atlas are clear. In both cases, an observation defies expectations. In both, a natural explanation exists, but requires citing unusual conditions. In both, the more compelling interpretation, life on K218b, artificiality for 3I Atlas, remains speculative until more data is available. And in both, institutions are walking a tightrope between reporting findings and avoiding hasty conclusions. NASA's communications about K218b have been very measured. They released the data. They noted the DMS detection. They emphasized the need for further observations to confirm, and that alternative explanations must be ruled out. They did not declare, "We have found extraterrestrial life," but they did not dismiss the possibility either. It is a classic lesson in scientific caution, acknowledging excitement while tempering expectations. Compare this to the narrative of 3I Atlas. Minimal updates, limited engagement with unusual claims, emphasis on the blackout phase rather than the scientific appeal. This difference may be strategic. Exoplanet atmospheres are distant, abstract, harmless. Interstellar visitors are right here in the solar system, close, immediate. It may be that NASA thinks the public is more comfortable with speculating about life on a distant exoplanet, but more nervous about the possibility of artifacts nearby. Or it may be the difference is in the evidence. The K218b discovery, while still in need of confirmation, is based, at least, on data from professional telescopes that have been and are being peer-reviewed. The 3I Atlas anomalies, reported by independents, are largely based on amateur processing of publicly available images, but have not been scientifically validated. The former is easier to interact with than the latter. Either way, the K218b story offers several lessons. Transparency builds trust. NASA releases Webb data quickly. They hold press conferences. They invite questions. They acknowledge uncertainty while providing context. That openness doesn't wipe out speculation. The alien bacteria debate has raged, but it does ensure informed speculation. People have real spectrums, errors, alternative models. They can judge for themselves based on real information. The 3I Atlas situation is lacking that transparency. Independent observer claims are not publicly responded to. Data from alternative instruments are not contextualized by NASA. The gap is filled with speculation, some well-founded, some not, and that erodes trust in a way that transparency, however uncomfortable, would not. There is a broader point about how institutions deal with surprises. Space science is full of surprises. Every time we point a new instrument at the sky, we see something unexpected. Sometimes it is a small, easy puzzle. Sometimes it is a big challenge to current models. And sometimes It is something that forces us to change paradigms, to change how we understand the universe. The history of astronomy is a history of adjusting expectations. We thought the universe was static. Then we discovered inflation. We thought galaxies were the largest structures. Then we discovered superclusters and cosmic filaments. We thought planets were rare. Then we discovered exoplanets by the thousands. We thought fast radio bursts were just instrument errors. Then we confirmed they were astronomical phenomena. Each surprise forced institutions to admit they were wrong, update their models, and communicate revised understandings to the public. 3I Atlas and K218b are the current chapters of that story. Both involved observations that didn't fit into the boxes available. Both require patience, more data, careful analysis. Both tempt us with extraordinary consequences while also asking us to remain skeptical. And both test whether institutions can walk the line between past from early certainty and endless uncertainty. The outcome for K218b will be unclear for years. Webb has scheduled further observations. Other telescopes will join. Models will improve. Eventually, we will have enough data to say whether the DMS are likely biological or non-biological. Until we get there, we keep the possibility in mind, but don't treat it as a fact. The same applies to 3I Atlas. December observations will add to the data. The analysis will be better. The model will be refined. And then we will know whether the anomalies are real or imaginary, whether the objects are anomalous or trivial. Before we get there, we observe and wait, remembering that the universe is in no hurry to reveal its secrets, and the process of discovery is often messy and takes longer than we would like. In August 2025, a team at the University of Washington announced a breakthrough in automated sky surveys. They developed a machine learning algorithm trained on millions of telescope images to detect asteroids and comets that traditional pipelines miss. The algorithm looks for patterns of motion, brightness variations, and morphological features that indicate solar system objects, rather than stars or galaxies. The results are impressive. In a test run on archived data from the Zwicky Transient Facility in California, the algorithm flagged more than 300 candidates that the standard system had missed. Tracking confirmed about 90% were real, either unrecorded asteroids or known objects whose locations had not been updated. 10% were artifacts or misclassifications, an acceptable error rate for the new system. But one finding stood out. The algorithm flagged an object in the June 2025 images that had not been recognized by a human analyst or a standard automated pipeline. The object was very faint, near the detection threshold, and moving slowly, consistent with a distant comet or Kuiper Belt object. Closer inspection revealed it was an interstellar visitor, later confirmed as 3I Atlas after its formal discovery in July by the ATLAS survey. Machine learning algorithm detected 3I Atlas before official announcement. That is the team's claim. In the preprint, they argue the algorithm recognized the object in the June image, but the discovery was not submitted for human review until after Atlas was announced in July. Due to the large number of candidates, and limited tracking resources. This revelation raises the question: if AI saw a 3-eye atlas earlier, what else could AI have seen that humans missed? And could AI have detected anomalies during the conjunction that human-led analysis did not pursue? The UW team proposes retrospective analysis of coronagraph data and Mars orbiter data using their algorithm to find 3-eye atlas in the blackout window. They argue that machine learning is good at finding faint signals in noisy data, the exact problem that independent observers face. When stacking frames, if the algorithm confirms the detection during the conjunction, that would strengthen the independent claims. If nothing is found, that would suggest the independent detections are spurious. As of early November, the team is still negotiating access to the necessary data repositories. Coronagraph data is public, but massive, and not pre-formatted for machine learning. Mars orbiter data requires permission from multiple NASA units. The administrative wheels turn slowly, but this proposal highlights a broader shift. In astronomy, algorithms are becoming co-discoverers, not just tools. They don't just process data according to human-made rules. They learn patterns, recognize anomalies, make predictions that humans might not think of, to test. And as they improve, they challenge the traditional process, where humans decide what is noteworthy and worth investigating. This is important with 3-eye atlas-type objects, because human attention is limited and biased. We look where we expect to see things. We favor bright objects over dim ones. We focus on familiar sky. AI has no such biases. It treats every pixel, every frame, every data point equally. It finds what's on the edges, in the noise, in places we don't think to look. The downside is that AI can be fooled. It can learn patterns that are not real, a byproduct of training data or imaging systems. It can see hot pixels as asteroids, cosmic rays as comets, satellite streaks as interstellar visitors. So, the 10% false positive rate in the UW study is both impressive and worrying. 90% is great for a new system, but 10% wrong means that 1 out of 10 findings is wrong. Scaling this out to millions of images results in thousands of false alarms. Humans are still essential, but the process is changing. Instead of humans scanning each image, and sometimes missing, AI scans every image, and humans review. The AI flagged candidates. Faster, more comprehensive, and fewer human misses.